Welcome to video lecture M5. This one is on matrix operations. I'll be your ringleader, Tom Roby. Here are the outline and objectives. So we would like to understand matrix addition and scalar multiplication conceptually and be able to compute examples. This is not so hard. We'd like to know at least two different ways to multiply matrices and demonstrate why they're equivalent. So this is something we'll see in some examples. But one way is conceptually much better for understanding a lot of basic things in linear algebra. And finally, I want to conceptualize matrix multiplication as really representing composition of corresponding transformations, because that clears a lot of things up. So we have these really three different points of view on matrix multiplication, and we will see more how that plays out when we study the properties in an upcoming video lecture. But as far as matrix addition and scalar multiplication go, this is really dead easy. We should just think about these things as being kind of rectangular vectors, right? The thing that's beautiful about vector addition is that it just happens component-wise. And scalar multiplication, you just multiply each component, right? So if I want to do something like add A and B to each other, then what do I need to do? Well, A plus B is going to be a 2 by 3 matrix where I add 1 plus 0 and I get 1. I add 2 plus minus 1 and I get 1. I add 3 plus 3 and I get 6 in this component. In row 2 I add 4 plus 0 and I get 4. I add 5 plus minus 2 and I get 3. I add 6 plus 0 and I get 6. Okay? So that was easy enough. Now notice that I can't multiply, I can't add B and C, right? Because they're not of the same size. So maybe I just said, when can we add two matrices, right? That's the question. And so you can add two matrices if they have the same dimensions, if they're both m by n matrices for the same m and n. You can't add a 2 by 3 matrix to a 2 by 2 matrix. We will be able to multiply such matrices though, so that's coming up. Now, when can you multiply a matrix by a scalar? Answer, anytime, right? So you take any scalar. If I'm interested in knowing what, say, 2 times A is, well, all I do is multiply all these things by 2. So I get 2, 4, 6, 8, 10, 12. And so, if I just took all these numbers and laid them out in a single row as a vector, I would be doing the same thing. Okay, so this is not hard, and I don't think we need to dwell on it much. But let's think a little bit more conceptually. What matrix M satisfies the property that when I add M to any matrix A, I get back the same matrix I started with? Pause if you need to, but maybe you see fairly quickly that the M that we seek is just the matrix. Well, if I'm in the 2 by 3 world, it would be this matrix. But in general, just call the matrix 0 and assume that its dimensions are whatever dimensions it needs to be. We can specify them if we need to, but usually we don't. Notice this is not a vector. Vectors, even though the vectors of all zeros is a vector, this is a matrix of all zeros, and we're not writing it in boldface in the text, and I'm not writing it with an arrow over it in any of these video lectures. All right, and so now here's a proposition, and it's not hard to see what's going on in any of these things, right? So for example, A plus B is the same as B plus A, right? Because I'm just doing it component-wise. So whether I add 1 plus 0 or 0 plus 1 in the first component, I still get 1. If I add 5 plus minus 2 in that component, or minus 2 into 5, I get the same thing. So this just follows immediately from the properties of ordinary addition. And similarly for this one and for this one, if I add 0 in every component, I don't change anything. Here, if I rescale the sum of two matrices, it just boils down to this distributive property in every component. So the key thing to remember here is that because everything is just taking place component-wise, there's really not anything very exciting going on. It's all very easy to see. So I think that's all I want to say about that for the moment. And so I'd like to move on to matrix multiplication. So matrix multiplication, I really want to think about matrix multiplication as I have a vector x, and I want to know what happens if I take the product of two matrices and I apply it to x. Well, the property I wanted to have is that if I applied b to x and then a to x, I should get the same result as if I applied AB to X, right? So I could think about I take X, I operate by B. So X has to be in some, so conceptually what's going on is I've got some blob here which represents R to the P, and X lives inside of it. And now from here, I go to another blob that I'm calling R to the N, and I go from there to another blob that I'm calling R to the M, right? So these are just these different spaces, and each matrix corresponds to a linear transformation, right? And so the first thing that I'm doing, because it's closest to X, is B, right? So first I'm doing B, and then I'm doing A. And so over here I have the vector Bx, right? So this guy goes from here to here, and then Bx goes over here to some other vector Abx. Okay, so X is in R to the P for some P, B is in R to the N, and AB is in R to the M. Now notice, in order for any of this to make sense, what are the dimensions of these matrices? So B is going to have to represent an n by p matrix. So this is an n by p matrix, and this is going to have to represent this is going to have to be a no, that's right. This is an n by p matrix. And then this is a m by n matrix. And what I'm multiplying is an m by n matrix by an n by p matrix. Right. So when I multiply an m by n matrix by an m by p matrix, I end up with an m by p matrix. Right. So that's something we'll see in more detail when I actually write out the definition for you. So here's the definition. Right. If B is an n by p matrix, so it's got n rows and p columns, so I call the column vectors, these are column vectors of length n, b1 through bp, then what am I going to do? If B were just a single column, if it were just b1, then the definition would be, well, ab1 would just be the linear combination of the columns of A given with the coefficients of b1. And so now what I do when I want AB, when I've got a bunch of different columns, is I just do the same thing. I concatenate all of these things. Okay, so let's see what I say. Each column of the product AB is a linear combination of the columns of A with weights from the corresponding columns of B. Okay, so all of these are linear combinations of the columns of A, right? But they're different linear combinations. This is the linear combination that's given by whatever this first vector in B was. And this is the linear combination of A given whatever the second vector in B was. Okay? And this is, whatever definition of matrix multiplications you've learned, this is really the best definition for understanding things in terms of linear dependence and independence and span and some of the algebraic properties that we'll see in a minute. Okay? So let's look at an example. Suppose I want to multiply this matrix A, 1, 2, 3, 4, 5, 6, very generic, times the matrix B. So let's see, does that even make sense? Well, if I took 1, 2, 3, 4, 5, 6, and I multiply it times -2, 1, 3, 2, then what I should get is, well, I need to take the -2, 3 combination of these two columns, right? So that means I need -2 times this column plus 3 times this column. So in that first column, I'll get -2 times this plus 3 times this. So that's -2 plus 6, which is 4. And the next entry, I'll get -2 times 3, that's -6, plus 4 times 3 is 12, that's 6. And then here I'll get -10 plus 18, so that's 8. So I get 4, 6, 8 there. And now if I take the linear combination of these columns with weights 1, 2, that means I take one of these guys and add 2 of these guys. Then I'll have 1 plus 2 times 2 is 5 of these. I'll have 1 plus 2 times 4 is 3 plus 8 is 11 of these. And I'll have 1 plus 2 times 6, so that's 12 plus 5, I think is 17. So if I did my computation right, which is always a, not a dicey thing, then the product of these two matrices is that. Now notice, You know, we already talked about when you can multiply two matrices. I can multiply these two matrices because the number of columns I have here is equal to the number of columns I have here is equal to the number of rows I have here. In other words, the size of one of these things. Because I need these to match, right? I'm going to take the linear combination of each column, so the number of columns here has to match the size of this vector. So for example, if I tried to do it the other way around, if I tried to multiply minus 2, 1, 3, 2 times 1, 2, 3, 4, 5, 6, think about what would happen, right? I'd be trying to take a 1, 3, 5 combination, but I only have two columns. Bam! You can't do it, right? So it's just not allowed to multiply. So here I had a 2 by 2 matrix, and I tried to multiply it by a 3 by 2 matrix. But the point is that these, if you think about it this way, these dimensions always have to match, and they didn't here. But up here, I had a 3 by 2 matrix, 3 rows and 2 columns, times a 2 by 2 matrix, and this guy and this guy were equal, and that's what I need. Here these guys were not equal, and that's bad. Okay? So that's the story for when you can multiply two matrices. And if you were thinking carefully about the computation I just did, you can actually see that there's another way to think about this, right? If all I'm interested in, for example, is, say, this entry to start with, this 4, how did I get this 4? Well, this 4 was the negative 2, 3 linear combination of these two columns. That was this whole column. But this entry was just the negative 2, 3 linear combination of 1, 2. And what does that mean? Well, that means I take negative 2 times 1 plus 2 times 3. In other words, the other way to think about matrix multiplication is that this 4 here is really the dot product of this row, the first row in the first column. Now, if I wanted to take a different one, let me find a different color here. Suppose I was interested in this 11. Where did this 11 come from? Well, this 11 was the dot product of, it appears in row 2, column 2, right? So that means I must have used this row and this column. If I take that dot product, I get 3 plus 6. 3 plus 8 is 11. Good. Right? 3 times 1 plus 4 times 2 is 11. All right? And so that works in general. And sometimes if you're doing hand computations of matrices, it's a little bit faster to just say that if I want the ijth entry of AB, right? Row 1, you know, so I mean, even if I wanted something like, let me do one more of these guys. Suppose I want this 17, right? Then that 17 was, it's the 3, 2 entry, right, of this. So that means I look at the third row here, and I dot it with the second column. So I'm going to take this row and dot it with this column, and so I get 5 times 1 is 5, plus 6 times 2 is 12, which is 17. Okay? Now, if you think about doing it the other way, you'll see that it's exactly the same thing. So this isn't a deep thing, but the point of view conceptually of thinking about matrix multiplication is just being a concatenation of matrix vector, taking the linear combinations, will be very useful later on. It really sets the stage. And books that don't do this for linear algebra, I think, don't end up not being able to clarify things quite so easily. Okay, so we've seen that matrix multiplication, the order matters, right? You can't even, sometimes you can only multiply matrices in one order and it's not even defined in the other. And we've seen a definition that generalizes matrix vector multiplication. And then we've got this finally row column rule for matrix multiplication, which might be the thing that you were first taught if you learned matrix multiplication earlier, but is not the most useful thing for this class. And I guess actually that's it for this lecture. Thank you for your kind attention.